Good afternoon, astro enthusiasts. This is the final installment of Primus Talks 2020. This event was hell of a ride, and we honestly were overwhelmed with your avid response. Team ARKA is really grateful for all your support. I am Anirudh Anand, a member of ARKA, the Astronomy Club of IIT Dhanbad. Today's session is kind of special. We have with us Dr. Rajesh Sadanandan from Indian Institute of Space Science and Technology. Dr. Rajesh is currently an associate professor at the Aerospace Engineering Department, IIST. He completed his master's from IIT Madras and went on to pursue his Ph.D. from the University of Karlsruhe, Germany, to eventually work as a scientist there for 6 years. He has significantly contributed to a few aerospace propulsion projects of ISRO and has even filed a patent for a non-premixed gaseous fuel burner. He is a technical connoisseur who actively builds a future over an absolute mastery of strong underpinnings. The talk would give meaningful insight into the current state of affairs and anticipated developments with regards to aerospace propulsion in the foreseeable future. The format of the session remains the same, with the first part featuring a presentation from a guest speaker, followed by an interactive Q&A session. For the latter, the audience is requested to drop the questions in the live chat box, which will be picked later on. So without much further ado, let's invite our honorable guest speaker, Dr. Rajesh Sadanandan.
Hi, hello. Good afternoon, everybody. Thanks for the invitation from IIT Dhanbad. I'm glad to be here, especially on a weekend. Whatever I'm going to present is basically an overview of the aerospace propulsion. It's very fundamental in nature. Let me introduce myself. Addition to whatever the host has said about me. I work an associate professor in IIST. My areas of research are basically in propulsion, but I also work in some clean combustion devices and also try to develop diagnostics, especially optical and laser-based diagnostics for research. These find a lot of application, not just in aerospace, even though I am coming from aerospace department, but also in any kind of propulsion devices. Basically, power generation works also on the same kind of technology. So here today, what I will basically concentrate about is aerospace propulsion, which is basically I have slides taken from what I was teaching in the institute for BTech and MTech students. So this is kind of a cherry picking. I will only take a few slides from here and there because I wanted to make it as fundamental as possible, because I presume there will be a huge amount of audience who are not really from an aerospace background, but probably from mechanical or basically some enthusiasts in aerospace propulsion. So I'll try to keep it as simple as possible. So I'll start. The overview is like this. I'll start with the history, basically what propulsion means. And then concentrate on what aerospace propulsion, what is it, how is it different. And then maybe one or two slides, I will go a little bit deep into, for example, performance, or just to try to introduce the terms that you usually hear in the news and all those things. Okay, so that the next time when you hear about it, you will be or at least you will see that, yeah, I heard it somewhere kind of thing. Okay, so that's what the content is. Before I jump into my presentation, just for me, my intention is just to motivate you guys. Okay, aerospace is not very common field, even though it has some catchy title name and all those things. And now with a lot of rockets flying around, it may be very interesting. But still, if you look into the career choices made by the students, especially in India, it's not really aerospace, because obviously the job opportunities are very, very less, extremely less when compared to, say, mechanical. But times are changing, and now you see a lot of startups coming around, and ISRO is changing policy. It's no longer the dominant player anymore, or they want to spread the facilities to who is wanting to become the next Elon Musk. So I think with all these startups coming around, and many of our students are already working in some of these startups, so it's not ISRO or governmental agencies who are the sole job providers. There are private companies as well. How far these companies will go, that is only time will tell, because as you know, it's not a simple technology to master. But those who are interested, I just want to give an overview of what is there, what you can try to achieve, kind of thing. But the career choice is yours. I just want to motivate you guys on aerospace propulsion, because that is one thing I am very much fascinated on. I'm a hardcore aerospace guy, even though my knowledge is very limited. But anything that flies just simply fascinates me. So I try to trigger at least one or two people some similar kind of passion. I'll be more than happy if I have succeeded in that. So this is the basic idea of this talk. Okay. Thank you, Anirudh. So is it, now I can jump into the presentation, or is it?
Yes, sir, sure.
Yeah, okay. So I'll share my screen. That's basically the slides. Okay, I hope the screen is visible now. The slides.
Yes, sir.
Okay. So this is what it is all about. It's a very basic introduction about aerospace propulsion. When people talk about aerospace propulsion, this, or at least I think today's audience, many of them will be thinking that it's all about rockets. Also, I have accidentally put a rocket of ISRO in the title slide, but it is not all about rockets. Okay, so aerospace propulsion, when we talk about it, it's basically divided into two. Okay, it's broadly categorized as two. One is air-breathing propulsion, and the other is rocket propulsion. Okay, so because whatever engines we talk about, the ones we fly in commercial airlines, and it's still aerospace propulsion. It is still something flying, but there the engines used are what we call it as air breathing, as the name suggests. It is breathing something from the atmosphere. Basically, air is taken from the atmosphere. Whereas in rockets, as you know, it flies to the outer space. It flies only for a short duration of time in the atmosphere where air is available. Afterwards, it is no longer there, so it's still in the outer space. It's vacuum. So for the flames, which are basically the heart of the engine, for the flame to sustain, you need oxygen or the oxidizer. So the rockets carry the oxygen along with them. Okay, it's not sucking in air from the outside, but it is actually stored in cylinders inside the rockets, which is used for the firing process, or technically, or we call it as combustion process. So in air breathing propulsion, air is taken from outside, whereas in rockets, it is carrying it along with the rocket. So what we talk about is basically these two parts. One is air breathing propulsion. We talked about a little bit about what is out there, what is the kind of engine that you usually see in commercial airlines and all those things, before jumping into the second half, which is the rocket propulsion. Okay. Before going into that, we'll just introduce the word propulsion. Propulsion, the word comes from the Latin word. It is called propellere, where pro stands for forward or before, and pellere is push. So together we can say propellere or propulsion is pushing forward, or it is basically you are changing the act of motion of a body. Okay, so that is act of changing the motion of a body. That is what the propulsion means. So in that regard, even automobiles is a propulsion device. Okay, automobile engine is a propulsion device because you are changing the motion of the body. So there is way aerospace, when it comes into the in front of it, you say it as it is the propulsion device being used for aerospace application or flying applications. So air breathing, as I said before, utilizes mostly surrounding medium as a working fluid, along with some stored fuel. For example, turbojet, ramjets, and all that. The fuel in commercial airlines, if you look at it, it's actually kerosene. It is called jet. It's a purified form of kerosene, which mostly being used. Whereas in rocket, the fuel, there are a wide range of fuels being used, which will be coming up. We'll be talking about it in the second half. So rocket carries its own propellant device that produces thrust by ejecting stored matter, because all the propellants, the fuel used in rockets, we usually call it as propellant. Okay, whereas in in aerospace application or air breathing application, we don't usually call it as propellant. We just call it as fuel. Okay, but when it comes to rocket, we just call it as propellant. But it's the same. It basically means propellant. But propellant in rocket has the slight differentiation. When we say propellant, it's not just the fuel, but we are also talking about the oxidizer. So it's basically both fuel and oxidizer is called as a propellant in rocket. Whereas it is not in air breathing. So rocket propulsion is an act of imparting the momentum to the object in space. Here the key word is space, okay, because since it is space, we have to carry the fuel. So the first part is about air breathing propulsion. This is a simple schematic here where you can see the air the engine is breathing air from the atmosphere. So something goes in and then there is a jet of fluid coming out, which provides a momentum forward, whereas in rockets this part won't be there. Okay, so there is no breathing happening. So we'll have look into a just do a sneak view of the history of propulsion. All this, irrespective of aerospace or like marine propulsion or in earth propulsion kind of thing, everything comes from the fact of the human ambition or the human will to move forward in a much faster speed, or just go from A to B at the shortest time possible. That's what our goal was. Even from the prehistoric times, earlier we used to walk, then run, and then you see that the animals are moving faster. How could we move faster than that? So at some point in time, they realized, okay, there are animals who can run faster than us, so why don't use them? So that is where like domestication of horse, and there are bulls and all those things happened, which basically made our movement easier. We can sit on the top of them and use their energy to move forward at a much faster speed. So that is where the it's all as a means for transportation. It is nothing more than that. So there, then later on stages, we invented the wheel, which was a huge invention at that time, because you think that shape can do, how we can move forward just by changing the shape to a circular thing. Okay, so we realized that, okay, add some the power of the animals to the wheel, that is like a chariot or cart or something, then we can move farther distance, not as a single person, but we can also put a lot of stuff into it. We can carry mass movement is possible simply because of the invention of the wheel along with it. And in the 20th, fast forward the 20th century, motor vehicles came into the picture. Then it is then the propulsion technology, that's what's the engineering side started showing up. Okay, then it was moved to ship technology because of people's willingness to explore things, exploration, find new land, mostly for commerce. It's maybe the ambition is to travel and all those things, but there is always hidden agenda. For earlier it was mostly for commerce, and later on it becomes all this transportation, whatever we're doing, it's for military applications as well. There's human greed starts showing up. So if you look into aerospace propulsion in such, it is basically, we started seeing birds and we want to fly. That's as simple as it is. So you might remember seeing the grainy images of people putting on some wings, artificial wings on the hand, and trying to jump from cliff, trying to imitate the bird and all those things. That's all our ambition to fly. Okay, if the birds can fly, why not us fly? Okay, it's the same. And it became successful with the Wright brothers' first flight. It was only for a short duration, but still it was historic. That revolutionized our transport system. Okay, then massive improvements come throughout the history, irrespective of which technology you take. Okay, massive progress in technology comes during war, because that is our human wiring comes in the form of greed, and we are always good at killing people. I mean, that is where the technology moves fast forward. Okay, anywhere in the history you see that it's always the military targets, military ambition that is accelerating the progress. Okay, aerospace propulsion sadly was no different, and you will see in the First and the Second World War, First World War with the propeller aircraft, Second World War with the jet engines, revolutionized the aerospace propulsion. And now we have high-tech, low-polluting, very efficient engines for our military applications as well as for civilian application. Okay, so that is just a sneak preview of the history. Now we'll go into how these aircrafts fly. Okay, so aircraft, there are different forces acting in the aircraft. As you know, the engine provides some thrust, so that's moving forward. That is the thrust produced by the engine. But the body of the aircraft and everything we have, it's not an ideal process. There is always losses associated with it. There is some resistance to the flight. That is what is in aircraft terminology, we call it as a drag. Okay, so the thrust is balanced by the drag. Only when you overcome the drag, you are going to get a forward movement. Okay. Similarly, if you are talking about flying, there is always a weight that is going down, and you have to create some kind of a force up. Okay, to create that flying movement. That is what is called the lift. So the lift is always counterbalancing the weight. When you have the lift more than the weight, you are flying. Okay, and this is achieved by a nicely engineered structure in the wings. It is called an aerofoil. You can see it is not a flat disc or something. It is basically a condor shape. You can see the condor here. We have a flat lower profile, and then there is a condor surface on the upper side. This is purposefully done because so as to create, when you have a longer distance, the air flowing through this top surface has to travel a longer distance when compared to the air flowing underneath the aerofoil. Okay, so that means at this point, it has to come at the same time. So that means the top flow has to move at a much faster velocity. Okay, higher velocity means you are producing a lower pressure in the top surface when compared to the lower on the bottom side. That means you are creating a pressure differential. A lower pressure, higher pressure at the bottom, lower pressure on the top. That means there is a net resultant pressure force towards the top, and that is what is called as a lift. So you have in aircraft the wings is a component that provides the lift, and it has to be carefully engineered so as to create the lift. So that means for an aircraft to fly, first you have to create a momentum forward. So you have to run, you have to move forward so as to create a flow like this. And when the velocity is sufficient enough, the structure will start creating the lift to fly. Okay, that is why you need a runway. Okay, so because the runway is where the pilot accelerates, give the stick forward, and it moves accelerate forward. That is to create this huge amount of velocity over the aerofoil, so that after some distance, that the aircraft can fly or create a lift. Sufficient lift is produced so that the aircraft can fly. Okay, so this is basically how the aircrafts fly, or what are the forces associated with the aircraft. And then there are, you might have seen, it is not just jet engines that are flying, but there are also propeller engines. Even though I said it was propeller technology came into being in the First World War, but we are still using it because there is obvious advantage of propellers when compared to jet engines. For especially propeller aircrafts are much more efficient at lower flight speeds than when compared to the jet propulsion. Jet, as you can see, it needs a sufficient amount of velocity to go inside and come out. So it's whatever momentum the jet propulsion engine creates depends upon the air, that is the velocity of the air coming in. Okay, so at lower velocity it produces lower thrust, and at higher velocity it produces much more higher thrust. So jet engines can be more efficient at higher speeds than at lower speeds, whereas propeller aircraft, which is much more efficient at lower speeds than in higher speeds. Okay, the huge propeller sitting in the front, it can, when the fan rotates or the propeller rotates, it can suck in a huge amount of air. Okay, so that creates that huge mass flow rate of air will help in producing a massive thrust. So the propeller aircraft, it accelerates a huge mass flow of air to a lower velocity behind, whereas in the jet propulsion, you can see the inlet is small when compared to propeller. So it accelerates a smaller velocity, smaller mass of air, but it is capable of accelerating at extremely higher speeds than a propeller. Okay, so there's basically a slight difference between the two. One is good for low velocity application, the other is for higher velocity applications. Okay, so there are different engine concepts if you look into it. So these are like, we started with what is called a piston engine with propeller. Piston engine is something similar to our automobile engines. These are the ones that have been working in the earlier stages of development, especially in World War I and all those things. It's a complicated system. You might have seen in some museum, you can still see the piston engines, like the collective piston, some 8 to 10 piston engines sitting along the circumference of a circle, and then providing power for the propeller. Okay, that changed when and the gas turbine engines were developed in the 1940s. Okay, the turbojet engine that revolutionized the aircraft industry, or the engines are working. So these are the different types. One in the MIST, it's mostly based on what is called a gas turbine or turbojet engine. And these other different things that are written here, turboprop, turbo shaft, turbofan, these are all just a variants of a gas turbine. So I'll just talk about only the gas turbine, how it works, and then maybe on a slide I'll show how all these things works. Okay, so I'll concentrate more on how the gas turbine works. That is how our commercial airlines' engines are. And even in military jet aircrafts, it is still the gas turbine technology with some modifications kind of thing. Then there are new engines under development. Okay, recently you might have heard about DRDO sending the hypersonic scramjet engine successfully test firing and all those things. So I will just a couple of slides on what that is. Okay, and then these are like pulse jet. This is no longer in use. It is used in the World War. And then there are hybrid engines also currently under development. I might have one slide on that. Okay, so jet engine. Jet engine, it is also called Whittle engine, but it is developed in the 1930s. It's not just Sir Frank Whittle who developed the engine, who invented the engine, but there is also someone called von Ohain, Joachim Pabst von Ohain. He's a German guy, and he's from UK. They were actually parallelly working on the same concept side by side, and they came up with this jet engines almost at the same time. So the patent is awarded to both of them actually, and it works on a thermodynamic cycle called a Brayton cycle, which basically tells how the air that is coming in, what are the thermodynamic property variation that it passes through the engine once it comes out. So that cycle is called a Brayton cycle. Basically, all this propulsion device works on the fundamental Newton's third law. For every action, there is an opposite and equal reaction. So, and here you have a schematic of a turbojet engine, or that is called the Whittle's engine, the initial configuration. So what you see here, you have the air intake. This is the front end of the engine. Air goes in, and there is a compressor which compresses the air to extremely high pressures. Okay. And that high pressure is sent into a kind of a can, or it's called a flame tube. It's called a combustor. That is where the high pressure air comes in. You inject the fuel and then burns. It is basically our engine. In car, when you call an engine, this is what happens. Fuel and air injected into a chamber and ignited. Okay, so that is what is a combustion chamber here. And then the hot gases at high pressures, it is sent to what is called a turbine. What the turbine does is the turbine allows facilitate the high pressure air to expand. Okay, during the expansion process, the turbine wheels turn and it generates power. Okay, so that power generated is used for running the compressor, because compressor is compressing a liquid. It means you have to do a lot of work. So that means you need an external power to do that work. Okay, so that power is given by the turbine. Okay, so the high pressure gas, as it expands through the turbine, it is not expanding completely, it is only partially expanding. Okay, and the rest of the pressure is the gas, high pressure air expands through what is called a nozzle. Nozzle is a device, its main purpose is to accelerate the flow. Okay, that's all a nozzle does. Whenever you say a nozzle, you can see the garden hose nozzle. Okay, what does it do? It just accelerates the water flow with the velocity of the jet. It's the same thing. Here, what it does is gas comes in, it accelerates the flow, and that's what creates a jet of fluid at extremely high velocity. And the reaction to this high velocity gases in the engine, the reaction force is what creates the thrust. Okay, so simple mechanism is you blow a balloon and leave it, and you can see the balloon going up in a random fashion, of course. But how is it flying? It's because the gases the gases at high pressure inside the balloon comes out through the small hole. That is a high velocity jet, and that gives the thrust to go up for the balloon to move up. Same principle, nothing different here. So unlike a car engine where you say only this combustion chamber, jet engine has different components doing some different jobs. Okay, what the job done by different components is based on this Brayton cycle. Okay, so this is a blown up image of a turbojet engine, and you can see what are all these things, all these blades and all those things. This is basically the compressor. Okay, so air coming in is through it. These are the different stages, or the different stages of a compressor. So there is a small increase in pressure across all these things, and finally you get a very high pressure when it comes out here, and it is sent into a combustion chamber, and then it is expanded. You can see the shaft connecting the turbine to the compressor. As the turbine runs, it provides the power for the compressor and comes out. Okay, so this is a Brayton cycle. This explains the thermodynamic cycle behind this turbojet engine. So this A to B is basically the compression process. What is shown here is a pressure versus volume. Okay, so the air pressure goes up, that is, it's compressed. So it is compressed. So that is why the volume is also coming down. And from here, you add the heat that is in this process. This is B to C is the combustion chamber process. So heat addition, high temperature at extremely higher pressures. And then this is where the thermal energy available in the fuel is given to the air, okay, high pressure air. So now we have air at high temperatures, high thermal energy, and also at high pressures, and it is allowed to expand through the turbine. So C to D is expansion process through the turbine plus the nozzle. Okay, it's not just turbine, maybe only halfway through, and then the rest is through the nozzle kind of thing. So when a gas expands, it gets automatically cooled down. So that is why the pressure, this process is a cooling down process. Okay, so the pressure comes down, volume increases, expansion process, volume increases, and all those things. A turbojet engine, when compared to a propeller engine or other forms of piston engine, it's simple in construction, but you have complex thermo and aerodynamic problems, because here we are having a high pressure air and high temperature. That means the blades, it's whatever that is coming out here is at extremely high temperature. You need the turbine blades should be able to withstand that kind of temperature, which is not easy. Okay, so we are looking into something like 2000 Kelvin. That is the current limit now. So you need to have material that can withstand that kind of temperature. So that is the limit of the performance of a turbojet engine. Material limitation, actually. It has high operating temperatures, and it operates at extremely high speed. These turbines are running at, I don't know, maybe some 10,000 RPM or more than that, 20,000, 30,000 RPMs kind of thing. It's very high speeds. Okay, so this is a jet engine, aircraft engine. Whatever you see in the airlines, they are all, the core of the engine is having this construction. The only difference is what you can see in the different forms here. Turboprop is basically, you can see this portion is a jet engine. Okay, and the only difference is there is a propeller sitting here. So what it does is the jet engine is used to generate power to run the propeller. So majority of the thrust is produced by the propeller, and the jet engine, what it does is just to give the power to turn the propeller. Okay, so there is a jet coming out here, but the thrust generated is very, very less when compared to the propeller. Turbo shaft is almost the same thing, exactly identical. This is for helicopters. It's actually vertically up. And you have the huge fan of the helicopters coming here, but exactly the same kind of operation. The commercial airlines, what we see here is are basically a modified version of a turbojet engine. So what you see here, this is a turbojet engine, this portion. In addition to that, there is a propeller or a fan sitting in the front. Basically, you can think of it as a turboprop with a casing around. Okay, so you have here the propeller is outside, but here the propeller or the fan is inside. Okay, so what it does is, because you have a propeller, you can bring in a huge amount of air, unlike a turbojet engine. But not all the air goes through the engine. A turbojet engine, it is bypassed. Okay, so there is this. That's why it is also called a bypass engine. Okay, or a turbofan engine. So it splits into two stream, bypass stream and a core stream. Okay, so this increase in mass flow rate will create additional thrust required, and also the velocity increment coming here is much lesser than a pure turbojet, but in turn it helps in improving the efficiency. So all the commercial airlines build civilian aircrafts, you usually see turbofan engines. So ramjet, to be careful about the time here. Okay, ramjet, this is when compared to the jet engine, you can see all the complicated structures. Here there is nothing. It's actually a pipe with a fuel injection inside. That's it. No moving parts. It's very simple. One of the simplest engine configurations you can think of. So how does the combustion is achieved? So here you have air coming at very high velocities, and there is a ramming effect. Basically, it's basically the air is, you have a geometry that does the compression. Okay, so the geometry is configured in such a way that you have a ramming effect, and so it raises the cup pressure, and then you have the fuel injector, and then there is a nozzle that is accelerating the flow. So you take away this thing here and the turbine here. All is left is this pipe with the engine and a nozzle. Okay, the main obvious disadvantage is that you need to have a flow coming inside through the to have the ramjet engine to work. So it cannot start from still. It has to be already be flying at some velocities. Then only the ramming effect will start taking into effect. So this you will see applications in missiles, military application. Basically, this will act as a second stage of a missile or something, where the first stage will bring this engine to some velocity so that the ram effect can actually take place, and then in the second stage it will take over, kind of thing. Okay, simplest, no moving parts, relatively high temperature limit when compared to gas turbine engines, because there's no turbines or anything. Temperature limits are not coming into picture, so it can go to higher temperature than a gas turbine engine. Obvious disadvantage, it's not self-starting. It has to be brought to high velocity by means of some boosters or something. Okay, but it's very simple. It's just a pipe with a fuel injector. Okay. Scramjet, this is what you might have heard recently. DRDO tested a scramjet engine, and earlier ISRO has tested a scramjet engine successfully. So what is a scramjet? It's basically the same thing. It's a ramjet where in all these engines, the flow through the engine, the velocity is at subsonic. It's a very slow moving flow inside. Once inside the engine, it's slow moving. Okay. Why is it slow moving? Because in order to light the flame, you cannot when the wind is blowing, it's difficult to light a candle. It's the same thing. Okay, we slow it down so that the flame can stabilize. Okay, so it's almost in all cases here it is subsonic. Okay, but in scramjet engine, here the engine here you can see this is that ramjet configuration, or it's a pipe through which air is coming in, ramming effect and all those things, and this is a combustion chamber. But in this case, it's a supersonic flow that is going in. Because this ramjet, in principle, it looks nice, but it is effective only up to a certain Mach number, only up to supersonic flow speeds of Mach 4 kind of thing, beyond which it is not very efficient. Okay, because of a wide range of reasons, most important being that there is a huge pressure loss, because when you have supersonic flow coming here and you are reducing it to subsonic, there is a huge pressure loss which is obviously lost. And also the temperature being very high, there are dissociation losses. Dissociation absorbs energy. So that means you may not be getting the temperature that you like to have at the exit at supersonic speed. So the ramjet will be hugely inefficient when you go behind after Mach 4 or something. So that is why what in scramjet what they do is, okay, we don't slow it down to subsonic speeds, but we'll maintain some kind of supersonic speed. Usually it's around 1.2, 1.5 Mach number, so that this huge pressure loss and all those things can be avoided. And then the rest is the same as here. But if it works, when it works, you can think of taking up to something like Mach 20 or something like that, or hypersonic, extremely high hypersonic speeds. But this engine, people are trying to level for close to 60 years now. Okay, we still don't have a real working, stable engine anywhere in the world. Okay, the reason for that is the common phrase people use in aerospace field is that it is like lighting a candle in a hurricane. Okay, supersonic speed, you had to have a flame ignited and stable. Okay, which is easily said than done. Okay, it's a hugely complex process. When you talk about 1.2 Mach number engine inlet, from here to here, you get hardly a millisecond time. That's all. Within a millisecond, you want to ignite the flame and make it stable, which is a hugely complex problem. Okay, that is why people are still working. We still don't have a stable engine running. Technology demonstrated, ISRO has demonstrated, DRDO has demonstrated, US has done it long time back, Russians have demonstrated. Technology is demonstrated, but make it into a stable engine is still a hugely complicated task. Okay, so this is the scramjet engine that you will be, but this is the future, I guess. So what is the advantage of all this ramjet scramjet? Why can't we stick on to turbojet engine? So this I would like to show it in terms of this trajectory. Flight trajectory is shown here. Commercial airlines is what is shown here. Okay, 9 to 12 kilometers above the Earth. That is where the commercial airlines are flying. That is where the atmosphere is. It takes in air from outside and all those things, breathes and runs. But if you want to distant go very far distance, you'd obviously like to have move at a higher speed. That means you need to move in supersonic speeds. Okay, but in atmosphere, supersonic speeds is impossible because of huge aerodynamic losses, aerodynamic heating. So you have to go into outer space. Okay, so that is where rockets come into the picture. Rockets, you go into outer space and then comes back. But the problem with rockets is like if you look into a rocket engine, almost 35% of the total weight of the rocket is actually oxidizer weight. Okay, the carrying the oxygen, that is what taking the whole weight. Okay, so the idea is that anyway the rocket is flying through the atmosphere, why don't we take in the air from the atmosphere during that short duration of period and use only oxygen for the remaining period? That saves a huge amount of weight. Okay, so that means the fuel consumption, everything can be reduced. Okay, so that is the idea behind it. So in that, while the vehicle is in the atmosphere, we use the air that is available in the atmosphere, and the rest of the time we'll use a rocket. So that is shown by this trajectory here, the red line. Okay, so we'll start like a normal turbojet to ramjet kind of thing in one, and transition to a scramjet, that is in supersonic combustion ramjet, so we can increase the speed to much more higher speeds. But that's only a small corridor. You're talking about around 20 to 30 kilometers. That is the range in which the scramjets can work. Okay. Beyond that, when we are going above when we leave the stratosphere, then we light up the rocket and then go up. So it's like a kind of a hybrid version. Okay, so you have the ramjets and then the rockets to take it apart. So in that way, you can reduce a huge amount of weight. Okay, save money, save fuel, and all those things. But you can also move very fast for the distances. So that is the idea behind that hypersonic space plane or something like that. Okay, hypersonic air breathing cruise aircraft. So there is currently one engine that is being developed. So this is, you might have heard about it in the news. It's not at running, but this is a concept of, it's called a Sabra engine. It's by Reaction Engines in UK. This is a hybrid engine. Okay, it has a rocket in it. You can see the rocket engine part in it, but the initial part is all ramjet. There is also a ramjet here. Okay, and the rest is a jet engine actually. Okay, so the heart of this thing is this cooler. Okay, when we are going at supersonic speeds, you have huge high temperature that is coming here, so it needs to be cooled down as fast as possible. So you actually need a heat exchanger, and they have only recently they have successfully tested their heat exchanger, which can reduce the temperature from 1000 to 150 degree within a hundredths of a second. This is hundredths of a second, means it is much more faster than the blink of an eye. Okay, that's how fast this heat exchanger processes. So what it does is, in the lower speeds, lower altitudes, there that is coming in, it's cooled down, it goes into, there is a small turbo compressor here. Okay, it's split into two. One part goes into the compressor and then goes inside the combustion chamber, where it is burned with the liquid hydrogen that is stored inside. So it's kind of a normal jet engine mode. Compressor, combustion chamber, expand through the nose. That's in lower speeds. And the bypassed air, I said only part of it goes through here. The remaining part is going through what is called a ramjet engine. You have a ring of fuel injection here, and there fuel is sprayed. That is basically gaseous hydrogen is sprayed into it, and it is ignited. So you have two modes of operation here itself. So it's a ramjet engine operation, jet engine operation. But when it comes to higher in rockets in space mode, then all the air that is this engine runs with stored oxygen and stored liquid hydrogen. So it's basically proper liquid oxygen, liquid hydrogen, cryogenic engine operation. Okay, so all these things shut down, it will run as a rocket engine. So it's a hybrid mode. So in the lower speeds, it can go to 0 to 5 in the atmosphere, and after that up to Mach number 25 in rocket flight mode. So what you are looking here is, you have seen in rocket propulsion, you are talking about different stages, but here it's a one stage, single stage to orbit. That is what is done here. The whole flight from here up to the space, all in one engine only. Nothing is thrown out or anything. That is, it's basically, you can use this engine if it succeeds, single stage to orbit and come back like an aircraft. That's what the target is. It's an ambitious project, but they are currently doing a lot of tests. Okay. So that is, the operational limits. I think I'm running out of time here. God. So these are the limits, Mach number limits, temperature limits, aerodynamic limits. Depending on what kind of engine you have, helicopters can only go to certain altitude, but jet engines go to higher altitude. But then there is a atmosphere that plays a part. Lift limit is there. But jet engines, I said there is a temperature limit because of the because of material limitations. But low flying vehicles, there is also, because the atmosphere is very thick, aerodynamic heating comes into the picture, so there is a aerodynamic limit. Okay, performance parameters. One is, of course, you want to have the maximum thrust. That is what is the specific thrust per unit for less amount of air flowing through it. That is a specific thrust. This is how you characterize a jet engine. Specific thrust, you try to maximize fuel consumption. You try to reduce it as much as possible. That is thrust-specific fuel consumption per unit thrust. Okay, and then there is a different kinds of efficiencies. Okay, so here is an engine. Thermal energy is produced. It is converted into jet kinetic energy. Since it is not an ideal process, there is always losses. Okay, so there is an efficiency factor coming here, and the jet is converted into a thrust forward. So there is one efficiency coming here, and that is given by this thing. Thermal efficiency is basically efficiencies between the thermal energy and the jet kinetic energy being produced. Okay, and the propulsion efficiency is how much of the jet that is coming out that is converted into the thrust forward. Okay, and the overall efficiency is between this and this. Okay, thermal efficiency to the aircraft power, so that is given by the propulsive efficiency into thermal efficiency. In addition, for propeller aircrafts, you have also thermal energy converted into shaft power and propeller power. So obviously there is a ratio coming there also, propeller efficiency. So these are the factors you can use to see how good your engine is. Okay, different efficiency parameters. And this is what I was talking before: airspeed versus propulsive efficiency. Turboprop, these are propeller aircraft which are much more efficient than at lower speeds than at higher speed. The higher speed, you can see it's coming down, whereas the jet engine, you can see it's a linear, almost a linear increase. Higher the velocity is, higher the efficiency is. But you can see the bypass, because of the bypassing effect, the fan sitting in front of it can improve the turbojet efficiency at lower airspeeds. Okay. Okay, so that is about aerospace propulsion. Now we'll go into the rocket propulsion. So this is different. Basically, the history, if you look into, the rockets, the Diwali rockets and all those things, those kind of rockets are the beginning. So the Chinese found the gunpowder, and then they realized that it can be used for flying objects. So they started using gunpowder. Again, military campaign is what that motivated them all the time. So this is what is shown here. They invented the gunpowder, and then the next 7th century is military application. Even the Indians used it. Best example being Tipu Sultan using rockets against the British. Okay, so military is always plays a key role in whatever kind of development that we are talking about. The pioneers in rocket propulsion, it's not Frank Whittle or something. These are the 3 pioneers. This is in the 20th century. These are the people who actually developed, or the reason for what the rocket technology what we see today. First one is, this is a Russian mathematician, Tsiolkovsky. He never worked in experience. He never did any experience, but he developed equations. It's to show that rocket propulsion is possible and it can be used for space applications, even the outside space, interstellar applications kind of thing. Okay, so if there is a rocket, there is something called rocket equation. Will be see it was derived by Tsiolkovsky. Okay, and Aubert worked on it further, or he gave a detailed version of that equations, and he even shown that you can use cryogenic engines for space applications. Where Tsiolkovsky shown how we can escape the Earth's gravitational pull. Aubert shown that you can use it for interstellar space applications, and we can use cryogenic liquids to achieve that kind of thing. Interestingly, his PhD thesis was rejected by the university. His PhD thesis talked about how rockets can be used for space application, but it was rejected. Funny. Then the actual engineer, he was also a physicist. Okay, but the engineer in this, the 3 of them, is Robert Goddard. Okay, so he is an American engineer. He was also a professor in University of Massachusetts. He holds close to 200 patents related to rocket propulsion, mostly related to turbo machinery used for rockets. And he is the first guy who's shown that who flown a liquid propellant rocket. Okay, I think it's around alcohol, liquid oxygen kind of thing. So he, from the engineering perspective, he is the one who contributed a lot, and the US, they bought back all his patents in the 60s for close to 2 million euros, $2 million or something. Okay, so these are the three pioneers we see today. But the practically what the rockets can do was shown by this guy, Werner von Braun. He's a German guy. He worked under Oberth. He used it for evil purposes, of course, during the Second World War. You might have heard the V2 rockets. This is a semi-cryo engine. Okay, it's basically he used oxygen, liquid oxygen, along with alcohol. And then the most impressive part of this rocket was it has a onboard guidance control. Okay, so you fire it up, and then the guidance control can accurately bring the rocket to the designated target. So that is, so they called it the V2, or it is called Vergeltungswaffe. It's called a vengeance weapon. So they had, this is what is shown here. So you have a propellant that is alcohol and oxidizer. This is liquid oxygen that is shown here. And it's basically, it's actually a kind of semi-cryo engine at that time. They used it with lethal force in the Second World War. And the US, after the World War, he smuggled this guy. He was a Pakka Nazi, to say. And he used slave labor, concentration camp. He used concentration camp for making his rockets. But after the World War, he was never prosecuted. In fact, US smuggled him to US, gave him all the facilities to develop their rocket program. Okay, so the father of the US rocket program is actually a Nazi, is Werner von Braun. And he used the technology to take people to moon. Okay, so whatever the Apollo rockets that you see that has taken people to the moon, it was actually based on his design. Okay, this is what he has developed for the monstrous rockets that took the crew to the space, to the moon. So this is the history. Soviet first launched the artificial satellite in Sputnik in 1957. Yuri Gagarin made the first human space flight. And in the biggest event was the landing in the moon, which was absolutely stunning victory for the NASA against the Soviets. But that is then for a huge amount of time afterwards, there was a long pause. Basically, you haven't heard some big things in the meantime, isn't it? So it's always the rockets going up, somebody doing spacewalks and all those things. Finally, in the recent years, some guy called Elon Musk came into the picture and revolutionized the space flight again. Okay, so he came up with what is called a reusable rockets, which still then was kind of a fancy term, because people thought, okay, it's nice to have reusable rockets, but it's a difficult technology. Then one computer geek came and showed, yeah, it's not really so complicated. I can do it. So that's what. So now with the space exploration is again into version 2 mode, right? Now everyone is thrilled. Everybody thinks that we can make a rocket, and there are new startups coming. If Elon Musk can do it, why can't we do it? Kind of thing. And you see, they had been developing new and new technologies almost like every 5 years kind of thing. First they developed the Falcon, and then the Falcon Heavy. Now they are looking into Starship going to the Mars, and it's all interesting times ahead. Okay, so we should also talk about what ISRO is doing. We had humble beginnings, but we had great ambitions as well. So we first launched our sounding rocket in 1963. You can see the first launching. It was so small and lightweight. It was actually transported using a bicycle to the launch vehicle in launch station in Trivandrum. You can see the next, I think the next time they used a bullock cart because it was slightly more heavier. But that's where we started. Okay, we also had our successes over the years. We launched our Indian satellite Aryabhatta in 1975, and Lohini, then the emptied, but still we are carrying a dead weight around. Yeah. Hello. Okay.
Yes, sir, you're visible right now.
Oh, okay. So just ping me when I am exceeding my time limit. Okay, because I think I have already crossed the time limit, so sorry about that.
Yes.
Yeah, I'll try. Okay. So the staging, the importance is that so you have a huge amount of flight, the path flight time in which you are carrying dead weight. There is no liquid inside, but you still have to lift up the whole weight. Okay, so it's like it's a huge loss. I mean, there is nothing, there is no need to carry those weight up to the space. So that is where you can throw away the empty stages and concentrate only on where the liquid fuel is remaining. And also the added advantage is once you remove the dead weight, then the vehicle can accelerate much more faster. Okay, because now you have a less weight that needs to be lifted up. So that is a reason for the staging. So you remove, so the optimum you will see around 2 to 4 stages in a rocket. So that is why you do staging. Okay, so for different altitudes you select the engine that suits at the surrounding medium atmosphere or whichever altitude they are flying. So that is why we go for different kind of propulsion devices here. So this is ISRO's latest launch vehicle. It is called GSLV Mark 3. It is a 3-stage vehicle, 2 solid rocket boosters, 1 liquid engine, and then there is a cryogenic upper stage. Okay, so it has a 4.5 ton capacity to the geostationary orbit, but in low Earth orbit it can go up to 10 tons. Okay, so rocket propulsion, there are fundamental, there are terms that I'll be using. One is momentum, push mass into, you know that mass into velocity is momentum. Then there is what is called an impulse. It's a change in momentum. Force is the rate of change of momentum. Basically, this is the Newton's law. And this is one term that you commonly hear about in news and everything. Whenever they say we have developed an engine, what is the specific impulse? Specific impulse I said is a change in momentum. So impulse delivered per unit mass of propellant. For the per kilogram of propellant, how much is the impulse that propellant can generate? That is what is called a specific impulse. If you use mass of propellant, the units you get is Newton second per kilogram, but usually you hear it as in seconds. So we say solid rocket engines, motors have a specific impulse of 300 seconds. So where does that come from? It is when we talk about in pace terms of weight flow rate. Instead of kilogram per second, you say in terms of weight. Okay, multiply with the gravity. So it's basically what it tells you is how much of the thrust is generated by the fuel per unit flow rate of the fuel. Basically, it tells you about how far the range of your aircraft is. Okay, for per kilogram when I burn the fuel, how much thrust it can generate. So that means higher the impulse, specific impulse, how the more efficient your engine is, or the longer range it can go. For example, solid rocket motors, I said it's around 300, whereas in ramjet or turbojet engine, it is around 1600. Okay, because you are breathing that. Basically tells you how the air breathing engines in terms of range, it is much more efficient than a rocket engine. Okay. So we can divide the rocket propulsion system based on energy source. We can say chemical rockets, nuclear rockets kind of thing, or you can say based on what function it does. Initially, if you're starting from standstill, we call it as a booster stage, and the later on stages, we call it as a sustainer, okay, altitude control, etc. Type of vehicle, we can call it as an aircraft, or if it is military application, missile, space vehicle, etc. Type of propellant based on the propellant solid, liquid, or hybrid, or we can have different size, type of construction, number of, you also say like 3-stage rocket, 2-stage, that is based on the number of stages it has, kind of thing. Okay, these are the different system classification. So this is where I said the Tsiolkovsky, he derived this equation, which is basically called the rocket equation. Rocket principle, pushing forward by constantly ejecting out material stored in it. Right. So this equation tells you that material, this is the initial mass of the rocket, final mass of the rocket. For that mass ratio, and for a specific, if you have a specific jet velocity coming out, what is the maximum increment in velocity that rocket can achieve? Okay, so this is what that expression tells you about. Okay, so this is derived by Tsiolkovsky in the 1900s, I think 1906 or something, when no rockets were flying. So he's a mathematician and he derived. But with this symbol, now the new equations are the more accurate equations are much more complicated. But this is kind of a thumb rule. You can use it quickly to figure out, okay, what is the incremental velocity my rocket can achieve. If my initial mass is this, when the complete propellant is burned, the mass is this one, the jet velocity is approximately that. What is a incremental acceleration my vehicle can achieve? If you look into the nature, there is a good rocket in nature. I mean, this is what you see is a giant squid, which works on a rocket propulsion principle, actually. So what the giant squid, how it moves forward is that it sucks in all the water and everything inside this huge body. Okay, pressurize it. I think it's less than a bar kind of thing, but it still pressurize it, and then ejects the whole water that is inside the body into this through the small nozzle inside the back of it. Okay, at extremely high velocity, and that's how the squid moves forward. So basically, nature tells you the rocket propulsion principle still is there, already there in the nature. So you can see this is around 10 to 14 meters. A grown adult squid will look. Giant squid will look. It's in deep oceans. You won't see it in the normal ocean. Okay. So I think I will skip this. Okay, we'll go directly into solid rocket. This here I'm going into the different kinds of rocket that is available. I talked about PSLV having initially solid propellant rocket motors, and that is what is schematically shown here. What does that mean? The propellant or the fuel used is solid. Okay, it's kind of a candle burning kind of thing. So, okay, so in which you will have solid fuel sitting here, and there is a hollow space somewhere. There are different cross-sectional configurations, but here it is shown like a hollow cone, hollow cylindrical construction. So here you will light up the flame, so the fuel starts burning, and then there is a pressure buildup inside. Okay, so the initial lighting is done by an igniter sitting at somewhere inside the engine, and the high pressure, which is allowed to expand through what is called a CD nozzle or convergent divergent nozzle, because the normal nozzle, just a converging nozzle, cannot create supersonic speed. It can create only up to a sonic speed, that is Mach number equals 1. If you want supersonic speed, then you need a diverging section behind. So that is what is shown here. Okay, so that is all it is in simple. It's very simple in configuration compared to other types of engines, but the only problem is that it can, once you light it, you cannot stop it. Okay, you cannot, there is no start stop capability. Okay, so that is a problem with solid rocket motor. Advantage is obvious advantage, or the most biggest advantage is very simple, but the biggest disadvantage is that you cannot start and stop. We cannot just say like a aircraft engine, switch off the aircraft engine for some time and light it up again. That's not possible. Once it starts firing, it burns through. Okay. So propellant chemical accelerator is nozzle, that is this one. Energy conversion, chemical to thermal energy, no feed systems or valves. That is makes it very simple. Okay. Here is about the nozzle flows. Like I was saying, Mach number definition is flow velocity to the speed of sound. Okay, so you might have heard Mach supersonic, that means Mach number greater than 1. Okay, sonic is Mach number equals 1, less than 1 is subsonic flow. Okay, so if you want to accelerate the flow, the normal way, if you look into the garden hose or something, when you squeeze the hose, you see that water moving at a much more farther distance. That means it's accelerating the flow. That's a common configuration. You provide a converging section that is shown here, and it will accelerate the flow. If you tilt it around, if you make a diverging section, it will decelerate the flow. Okay, so that is what happens at subsonic flow condition. Subsonic nozzle is actually a converging configuration, whereas a subsonic diffuser, that is decelerating device, is a diverging section. But in supersonic flows, it's actually the inverse. Okay, if you provide a converging nozzle to a supersonic flow, it actually acts as a diffuser. It will slow down. Okay, there you have to provide a diverging section. So if you have a sonic velocity coming into or a supersonic flow coming in, if you want to further accelerate, you actually have to provide a diverging section. Okay, so when you look into the engines like this, here you have a subsonic flow, and my goal is to get a supersonic flow outside. That is for rockets. What you have to do is first you have to accelerate to the flow to sonic velocities. For that, you'll use a converging section, and then from sonic you want to accelerate into supersonic. That means there I have to provide a supersonic nozzle. So rockets usually have these two combined, converging, diverging nozzle. That's what you're seeing here, converging, diverging nozzle. Okay, so this is what is shown here. This is a combustor, there is a converging nozzle, there is a diverging nozzle, and you can see the relationship here. Okay, along the axis of the nozzle, so converging, diverging nozzle. If your flow is subsonic, as it flows through the converging side, it will accelerate, but then it sees a diverging nozzle, it will decelerate. Okay, but if your flow is in such a way that you achieve a Mach number, you get sonic at this minimum area, then the remaining section will act as an accelerator, so you can get supersonic velocities at the exit. So if you want to accelerate a flow to supersonic conditions, you have to get a converging, diverging nozzle at the exit. Okay, so this is a typical contour of a rocket nozzle. It's called a contour or a bell nozzle to reduce the losses associated with it. And the solid propellant, I said there are different configurations because like I said, once it starts burning, there is no control. Okay, so but if you want to design your thrust according to the propellant that is burning, you have to come up with a different configuration of cross section of the propellant inside. That is what is shown here. There's the different kind of cross section. Basically, you can design any configuration of your own. Okay, and most commonly used is a star. Okay, so all the surfaces, it will be burning inside. So it will be, as the surface increases, okay, your burn rate increases because more and more surface is burning. That means the thrust will go up. Okay, so that means if you have a cylindrical configuration like this, over a period of time, you are continuously accelerated. Maybe for some purpose it is good, but for some purpose it may not be good. Okay, so that is shown here with respect to time, pressure, or thrust. This is what is if you have a cylindrical nozzle, a cylindrical configuration. So you'll have continuously, because the burn area is increasing, the inner surface area is increasing, you have the thrust that is going up. But if your rocket needs a continuously constant thrust, you don't want it to, then you have to be very creative. You have to generate some kind of a surface so that as the area increases, you still produce only the right amount of thrust. That is what is called a neutral. Okay, and then there are maybe cases where you have to be regressive, you need to slow it down kind of thing, then you have to design it in that way. So it's called a regressively burning propellant. And solid propellants are usually, it's the terminology sometimes people use is called a grain. It's a grain is nothing but a solid propellant. Okay, so this is a grain propellant grain classification. Liquid, as the name suggests, the propellants are liquid. So you have liquid oxygen and liquid fuel. That is in case of a cryogenic propellant, but if it can even be some other kind of thing like N2O4 that is very commonly used, which is not cryogenic, and it can be, the fuel is hydrazine. Okay, for example, the Vikas engine you might have heard from ISRO is having. So it has a liquid propellant engine, but it is not cryogenic engine. Okay, cryogenic engine is something different. So there, it's all in liquid stage. So what is the difference between that liquid and the cryogenic liquid? Cryogenic, the term cryogenic we use when the temperature of the fluid is below 123 Kelvin. It's easy to remember, 123 Kelvin. Below that temperature, if the propellant is stored, then it is called a cryogenic engine. Hydrogen, is a gas. Oxygen is a gas under normal conditions. So if you want to carry it, you have to liquefy it because it reduces the volume. Okay, hydrogen liquefies at 20 Kelvin and oxygen at 90 Kelvin. Okay, so both are below 123 Kelvin, and that is why it is called a cryogenic propellant. Okay, because it's are very low cold temperatures. So the engines that you are using cryogenic propellants are called cryogenic engines, whereas other liquid propellant engines, we could just call it as a liquid engine. But cryogenic engine is also a liquid engine. Okay, so we carry both of it in the form of liquid, and it expands through the rest is the same. You spray it into the combustion chamber and then burn and everything. It's the same technology. Just want to give you an overview. I talked about the engine that took the Apollo astronauts to moon. Okay, this is a sample of that F1 engine from the Saturn V5 rocket, and you can see the human here and how monstrous it is. I mean, like this is, I think this is the biggest engine that ever produced for space applications, and they had 3-stage engine. The first one was a semi-cryo engine, and the second and third stage were cryogenic engines, and each of this engine produced close to a lakh of thrust. Okay, 100,000, more than 100,000 thrust. Okay, the first stage had, I think, 4 or 5 of them, so you are looking into something like 400,000 thrust being produced in the first stage. It was a monster. It was a big, really monstrous engine. It's an amazing piece of technology. And you can see it was developed in the 60s and the 70s. I mean, we are now in 2020. We're still talking about going into the moon, isn't it? And this was with whatever technology that is available. They produced this monster engine taken up to the moon. Amazing piece of work. Okay, it's really good. And this is the injector plate. You can see all these small dots. These are all tiny injectors sitting here where the fuel and the air is sprayed into the nozzle. And this is what is shown here, the spray process. So one injector, you can see it's a hugely complicated problem. Okay, you have the liquid blob coming out and it is atomized into very, very fine particles. Then only you get a stable flame. So the injector technology itself is a wide range. It's a huge field. Okay. And usually all these rockets have around 100 injectors sitting here. Okay, this is around, I think, 110 injectors were sitting inside, and these are arranged in certain patterns and all those things. Okay, so that is just to get an idea about how these engines look like. Even the ISRO's liquid engines, you have close to 100 injectors sitting inside. Okay, it's not there is a reason why everything is called rocket technology. Okay, it's not an easy thing to master, but it's amazing thing. Okay, so this is what the hugely complicated process that takes place. If you take one injector, okay, liquid coming out, it has to be broken up into pieces. Okay, it first becomes a filament, then filaments into ligaments. It is called ligaments, and then ligaments are atomized into droplets. Okay, that's just the first part of the story. And these droplets then evaporates, so the fuel is produced, and the evaporated fuel then mixes with the oxygen. Okay, then ignited. That's when you get the flame. That's not, the story doesn't end there. That flame you need to stabilize. Okay, you need a stable flame. That itself is a complicated process. When all this series of process is successful, then you have a engine that is working stable. So now multiply it by 100 times, that is 100 injectors, and you can see where the complication is going. And then multiply it by the pressure. This was around 60 bar, but the cryogenic engines, you are talking about the chamber pressure of around 300 bar. So it's beyond our grasp, our human understanding how these things work. Okay, even now it's a hugely unknown phenomenon. Okay, so this shows the engine cycle. What it basically tells is what happens to the fluid inside a rocket engine. Okay, you might have heard in literature when you read the news and there are engines that are staged combustion cycles, gas generator engine, and all those things. Okay, I won't go into details. It's just simple thing. You have injectors, like I said here. That is, if you have a chamber pressure of 60, that means the injection pressure should be higher than that. So this fluid has to be pressurized to high pressures. How do you achieve it in rockets, in liquid engines? You have what is called a turbo machinery, or turbines are there, or fuel pumps and all those oxidizer pumps. Okay, there's a huge powerful turbines or pumps are sitting there. To run these pumps, you need some kind of a powering device, and that is done by, as usual, a turbine. Okay, so in order to drive the turbine, just like in jet engines, turbine, you need a combustion chamber that hot gases goes into the turbine. So you produce, there is an additional engine inside the main engine or outside along with the main engine, that is called a pre-burner or a gas generator. So its sole purpose is to run a turbine to provide the power for running the fuel pump or the oxidizer pump. Okay, so that you have the injection, sufficient power for the injection is done. So this is what is called a gas generator cycle. Okay, so the engine cycle, it can be open or closed. When these turbine exhausts are thrown out, it is called an open cycle. When they use this exhaust again for the main engine, it is called a closed cycle. Okay, so that is what is shown here. The exhaust from the turbine is not thrown out like here. It is actually sent inside the main engine. So here the difference is that you don't see a pre-burner in this configuration, right? The fuel, what they do is fuel that is coming in, it is running along the sides of the rocket nozzle because it is hot. Okay, so that if it is liquid hydrogen, it becomes gaseous and it develops pressure and it passes through the nozzle contour. Okay, so you have a high pressure gaseous thing that is coming out, and that is used to run the turbine. Okay, so you give away the pre-burner. Okay, so that makes it much more simpler. Okay, so that is what is called an expander, because it is expanded. The fuel flow is again expanded to run the turbine. But the most efficient is and the most complicated is what is called a staged combustion cycle. Here you can see there is a pre-burner and all this expansion cycle is also there. So it's a combination of these two. Okay, so here the fuel coming here, and that fuel again is used for running a pre-burner. Okay, so it produces an additional source of power. Okay, so the pre-burner drives the turbine, so you have the hot pre-burner exhaust coming out, and that is fed into the combustion chamber. Okay, the advantage is that these engines can run at a much more higher pressure than these engines, because you have the pressure that is developed from the pre-burner can be used here. Okay, that means higher pressure means you can reduce the size of the combustion chamber. You can make the combustion chamber smaller. So there is obvious advantage, but it's a hugely complicated thing. Most of the time you see this thing, gas generator cycle. Okay. So rocket propulsion, the parameters, we talked about the parameters of interest in aerospace propulsion, air breathing engine. Rocket propulsion, as I said, it's ISP. Okay, ISP is what that tells you how good your engine is. Okay, solid rocket motor is around 300, better is cryogenic around 400, and all those things. Okay, so that is why what does ISP tells you? It's the thrust per unit mass flow rate of the propellant, and it is divided into two. Okay. There is one thing called C star, and there is a CF. Okay, C star is what is called a characteristic velocity. CF is called a thrust coefficient. Okay, what it means, I won't go into the expression. What it tells you, C star tells you. So if you look into the rocket chamber, I can divide this rocket engine into two. One is like combustor, where the fuel, everything is burning, and then the hot gases are expanding. That is the nozzle section. Okay, C star tells you how good your combustor section is, or C star tells you the propellant. You can come up with different types of propellant. The propellant that you have designed or you are using, how much pressure that propellant can develop for a given mass flow rate. Okay, so it tells you the pressure generating capacity of your propellant. Higher the C star, it can develop higher pressure. That's what the C star tells you. It's an index of performance of the propellant. Okay. And CF tells you, give for a given pressure, how much your nose, how good your nozzle is, how fast the nozzle can accelerate your flow. Okay, so that is basically the thrust is generated by this nozzle. Okay, so that is what the thrust generating capacity of the nozzle is described by CF. Okay, so you have the index of propellant performance of the propellant multiplied by the thrust generating capacity of the nozzle. That is in effect is your ISP. Okay, so if you want to improve your ISP, you have to come up with a highly efficient fuel. Okay, generate high amount of pressure and all those things, and a nice design of a nozzle that can contribute to the thrust. Okay, so this is what ISP is about. Okay, that is all about the main rocket propulsion. Then there are rocket propulsion technologies used for satellite propulsion. You know it. So this is basically a small rocket engine where the gases is used, high pressure gas expanded through a nozzle. It is an engine. Okay, so that is what is called a gaseous propellant rocket engine. It's used for satellite propulsion, attitude control, orbit station keeping, and all those things. Okay, propellant is storage pressure, high pressure gas expanded through the nozzle. And then there is hybrid rocket, where it's hybrid comes from the fact that you have a liquid fuel used along with a solid fuel. Okay, so it's very simple. You have this is a solid rocket motor, and then it is supplied with a liquid oxidizer, sprayed into the solid rocket motor and ignited, and that is what is called a hybrid. There is one working engine you might have seen this. This is from the Virgin space flight. They are currently testing it. I mean, they have been testing it for a long time, but I think this year or next year it will be coming. So this is basically a common. These two are what is called the White Knight. It is a jet powered engine. It takes this rocket. This is a rocket here to a certain height. Okay, and there they use the engine that is being used in that rocket is what is a hybrid rocket engine. Okay, so it's similar kind of configuration, liquid oxygen. The advantage of this thing when compared to solid rocket is that here you can start and stop. Okay, when you switch off the liquid oxidizer, the engine stops, and when you spray it again, the engine can start again. Okay, unlike in the solid rocket motor. So that is why this is being used, but there are no other aircraft which are currently using it. But this is the only engine running, working hybrid rocket motor in the world. Okay, they are still testing it. It's not in full active duty, but you can see YouTube videos on that. Okay, then there are satellite propulsion rocket engines used. Basically, nowadays you can see electric propulsion engines being used. One of them, it is called, what does electric propulsion do? Okay, electric propulsion, unlike in the car batteries and all this car, it is a different concept. We use electrical energy to impart the thermal energy into the propellant. So here we are not burning the propellant. You use some gas, propellant gas, and then you use electrical energy to heat it up. Okay, for example, the arc heating electric process is one kind of device where you see there is an electrical source being used to heat up the propellant gas that is being coming here. Here is hydrogen, nitrogen, etc. Okay, so the electrical energy, it can be resistive heating, it can be arc heating or anything that provides the thermal energy for heating the thing, and the rest is like a normal thing. Okay, so this is one example of it. And another thing is this is called electrothermal thruster, because here you use electrically to heat up the propellant. Then there is non-thermal electrical thrusters. Okay, here you see you have a CD nozzle just like any other rocket engine, but here this is a ion engine, or it is Hall thrusters or an electric propulsion. ISRO has an engine that running the satellites, and you'll see many satellites coming up with electrical propulsion engines. And here you see this is not a CD nozzle, it's like a constant duct. Okay, what it does is a propellant gas. You use electrical energy to ionize the propellant. Okay, so you rip up the electrons out of it, make ions, and then use electromagnetic force to accelerate them. Okay, it's a slow process. Okay, it starts with a very small velocity, but then finally you get an extremely huge acceleration, and you can see the electrostatic acceleration can go up to 60,000 meters per second. Okay, so you have ions that are accelerated using these electromagnetic energies. Okay, and these ions, it is again sprayed with electrons to neutralize when it comes out. Otherwise, the vehicle will have a charge deposition in it. Okay, so here the electric in all these cases comes from here. It is for warming up the propellant, and here the electrical energy is used for supplying electrical power to all these devices, feed control, ionization device, and all those. Okay, that is where the electrical part comes in. It's a different from electric propulsion in automobiles. Okay, here we use electrical energy to provide some assistance to the thrust. Okay, the biggest disadvantage is, of course, you have to carry a high power electrical sources which are very heavy along with the engine. Okay, so that is the biggest disadvantage of it, to carry this electrical propulsion. You need extremely high levels of electrical power. Okay, yeah, that's all I have. Oh, I have gone up, I think. Sorry about that. I crossed by 30 minutes. It was not intended. When I talk about aerospace propulsion, I can't stop. Sorry about that. I hope I haven't bored you to death, but for me, it's a very motivating piece of thing.
Of course not, sir.
Yeah.
So thanks a lot for your enlightening and surprisingly comprehensive insights regarding aerospace propulsion. Your passion is clearly perceptible.
Yeah.
And sir, now if you allow us, we will begin with our Q&A session, shall we?
Yeah, sure.
Okay.
I'm not really an expert. I'll try to answer as much as I can. Okay, so I'm still learning.
So first question is by Karma. As we know that petroleum and various fossil fuels are limited and are going to extinct soon, what are the various fuels or propellants we are planning to use in the future?
Unlike in road vehicles or something, aerospace propulsion, hydrocarbons, there is we don't have any other option right now. Okay, so the hydrocarbon, at least till I retire, I'm almost sure that the hydrocarbons are the one that is going to drive this, because you are talking about huge amount of thrust to lift up these tons of equipment from ground. There is no other option. Okay, so you can use hydrocarbons, or like I said, the cryogenic the liquid hydrogen or something. The initial starting up, there is no other way. Okay, in the later on stages, maybe, I don't know, but currently I think at least in the next 20-30 years, I can't see any other propellant that is coming in. Okay, fossil fuels. Okay, hydrogen. There are other options, like coal is not ran out. You can create hydrogen from coal. So there are different options for generating hydrogen. Okay, so cryogenic propellants will still be available, kind of thing, but it's a different thing than in automobiles, kind of thing. But for the foreseeable future, hydrocarbons or like liquid hydrogen, like cryogenic, some kind of propellant, kind of thing. That's all. At least for the booster stages, there is no other option. Okay.
Aman Sharma is asking, for supersonic aircrafts, doesn't blast from the sonic boom damage the aircraft? How do engineers take care of such damages?
The blasting, it has already been solved. If you look into the military aircraft, it's already crossing over that sonic blast kind of thing. It's not an issue anymore. Okay, even the commercial airline Concorde, it was crossing from subsonic to supersonic, so it doesn't damage the aircraft. We are pretty much good understanding of how to overcome that. Okay, basically you have a shock wave sitting in the front of the vehicle, and that is going to heat up and all those things. But that is, materials and aerodynamics can take care of that. But re-entry vehicles still have a problem because you are extremely high amount of heating when it enters into the atmosphere. That is where all these heat shields and all those things comes into the picture. Okay, so anything that goes out of the atmosphere when it is re-entering, that heating becomes an issue. But again, it's a material problem kind of thing. But yeah, it's not an issue anymore.
Akshay Jain is asking, is the single booster system developed by SpaceX practically reliable for launch from other planet or moon? Are there any plans to commission it in ISRO or India?
Single booster system, I don't know what you mean by that. But anywhere, I mean, we are talking about, or SpaceX is talking about taking the vehicle to Mars and then coming back from there. Okay, so it can basically, as long as you have onboard fuel and oxidizer, it can launch from anywhere. It's not an issue. The question is, once it makes a long journey to Mars, close to a year, okay, then you need a fuel there to fill it up again. Okay, so that means there should be fuel storage already, or they should have transported fuel already there, or they should generate fuel there itself. Okay, so all the technologies in the future, what they're looking into, how can we generate fuel in there? So that's where we are hunting for, is methane available there, or is there any other fuel available there, kind of thing. Okay, so if you're talking about interplanetary adventure, of course, fuel availability of fuel is an issue, whether it is ISRO or NASA or anyone who is thinking about it. Of course, we have to find means of getting our own fuel. Okay, so it's no different whether it's SpaceX or ISRO, but ISRO is very, very far away from any interplanetary missions when compared to SpaceX. We are still at first master our space flights, or we would go to moon, manned mission, then only we can think of that.
So, Deepak Akela is asking, so what about our RLV? Is it working process is successful, or there are any default? And also why there is no booster?
I mean, the RLV is, so it was a technology demonstrator. It just wanted to show that, okay, we have master, or we know how it works, and it was tested successfully from whatever altitude they were trying it. But a technology demonstration is one thing, okay, but using it for a manned mission or irrespective of a manned mission kind of thing, for regular use, that's a series of tests that you need to do, like a flight like two demo. I don't know. I think it's the 3 times you have to demonstrate that it is working and all those things. Okay, but it's a completely different concept when compared to what SpaceX is doing. But from ISRO's point of view, yes, we have demonstrated the technology, we know it, but it is not at flight ready kind of thing. Flight ready in the sense we are not in a demo, or like what SpaceX is done, like they go up and launch in or land in anywhere in the planet, like whether it is in the sea or in the ground kind of thing. That kind of technology we don't have it yet, but I think that will be needed if we wanted to use it. But it's definitely it is in the pipeline, or it is for any space launch vehicle running companies. Reusable is the thing that you have to achieve. Okay, because without that reusable technology, you're never going to reduce the cost. So if you want to reduce the cost and compete with SpaceX, for example, reusable, you have to master it. There is no escape from it. Okay, otherwise you will run out of business out soon. Already we are seeing it, but yeah.
Okay, it's the last one. Shubhi Tiwari is asking, sir, what is the most efficient propulsion system for space exploration?
Space exploration. When you plan a mission or for any space agency, ISRO, NASA, or anything, there is nothing like a single engine that is good for everything. Okay, it varies in range of factors that comes into the picture. Example, what is your payload configuration, or what is the altitude that you want to go? How many stages are you planning, and all those. Okay, so like I said, PSLV has four different stages, and they are using two different kind of engines. And then if you look into Mark III, then there are three different kinds of engine. Okay, so based on what your requirements or what the customer's requirements are, you try to come up with a configuration that is the most competitively priced kind of thing. So we cannot use the most highly expensive, complicated engine technology for a simple mission when the customer is not ready to pay the price. Okay, so to answer to your question, most efficient propulsion system for space exploration, there is no single answer. Okay, depends upon what are you targeting. Are you targeting the moon, or are you, as your objective is just to launch a satellite in the geostationary orbit, or is it just for a low Earth orbit? Okay, if it is a low Earth orbit, then that's why PSLV mostly in the low Earth orbit, and you're not seeing any cryogenic engine going into it. It's not needed. It's a huge amount of complications. But whereas the cryogenic engine is used for geostationary orbits. Okay, so there is overall it depends upon the mission statement. Okay, what's your mission? How can we achieve that mission with the minimum cost? Finally, irrespective of whichever agency you're talking about, it's the money that rules. Okay, if you can save a penny, you'll try to save that penny. Otherwise, you are looking at a very grim future. Okay, it's all about money. Okay, if you can take out one screw out of my engine, then I will take that one screw out. That's the kind of competition we have. Okay, so there is no efficient propulsion system. If you are talking about like the good for the environment kind of thing, then I will say cryogenic with liquid hydrogen, liquid oxygen. No pollutants, fine. I'm fine. I'm happy about it. Okay, so, but there is nothing like, you can even use solar energy. There is something called solar sail, okay, which is used for JAXA, Japanese Aerospace Agency, have used it. It's a huge sail. Okay, it's kind of a wind sail kind of thing. But only thing is solar energy coming and hitting the huge sail, it's more accelerating it forward kind of thing. And they had a mission, I don't remember, I think it was for the Mars, Venus or something. They launched it, I forgot which year they launched it, JAXA has launched it. It's solar sail, it's still flying actually. It completed its mission, but it's like, it starts like a dead slow kind of thing. You can see because of the solar particles, charged particles hitting the sail. It's a small accelerator, maybe 0.1 meter per second pointer, but slowly it is keep on accelerating. And then it goes into extremely high velocity. It has reached Venus, and as far as last I heard, it is still flying. Okay, so there is no hydrocarbons or anything in it. It's just solar energy. Okay, so it just depends upon the mission. What's your mission is, and you bring up the technology. So if you can afford to wait for such long period till the sail reaches the planet, yes, why not a solar sail? Okay, so that's it.
All right, we are done. Thanks a lot, sir,
okay.
once again. We enjoyed this session a lot. We are honored to have you on our platform, and we are very fortunate to hear about aerospace propulsion from you live. And
Thank you for having me. Yeah, it's nice. It's my first webinar, but yeah, I couldn't stop. I should control myself next time. But yeah, thank you.
No, sir, we enjoyed it all through the end. It's fine.
Okay. Have a nice
now,
day then.
To the audience, this session concludes Primus Talks 2020. The series brought numerous fascinating cosmic aspects to light, a small effort towards creating an expanded consciousness in these trying times. We hope that you guys enjoyed it as much as we did. Also, don't forget to hit like and subscribe and press the bell icon below. Stay tuned to our social media handles mentioned below in the description, and don't forget to follow them and join us in our journey. Till then, stay safe, stay curious, space out.
Thank you. Good luck.